In this example, we're launching an object from the ground, so from the surface, and at a particular angle. So there's a little bit more math involved here than in our previous example where we're throwing something horizontally off of a roof or a building or some sort of height. So we should draw a very quick diagram just to give us an idea of what we're dealing with here. So we have our surface, which might be something like this. And as our question says, we're at an angle of 55 degrees to the surface. So that might be like that, 55 degrees there. And our velocity is going to be 1,500, and that's V1, 1,500 meters per second. So of course, given that we have a velocity at a certain angle, that must mean we have components to that velocity as well. So there's going to be a V1x, and there's going to be a V1y. We should, as always, solve these two components separately. So we're going to start by solving the vertical component of our question. So what do we know? Well, we know that V1y is going to be equal to V1, 1,500, times the sine of 55 degrees. So we can solve for that, and that gives us 1,229 meters per second in the up direction. So we're going to say that up and forward or up and to the right, depending on how you're looking at it, is positive, and then down and to the left will be our negative directions. Next up, we can also include the fact that we have acceleration due to gravity. So that's only, of course, in the y direction. And that'll be 9.8 meters per second down. Or, of course, you could say negative 9.8 meters per second squared, sorry, up, right? Because they're going to be opposites. Because this is presumably going to come back down to the ground at some point, because it is a parabola, right? So any given parabola is going to start like this and end like that. So it is going to come back down to the ground. We can say that our net displacement in the y direction at least is 0 meters, i.e. there's no net displacement. So we can solve this. Let's take a look at using our equation here to solve for time. The duration of flight obviously implies what time or how long does it spend in the air. So we can start off by looking at our change in displacement, and that is going to be equal to our initial velocity in the y direction times time plus 1 over 2 times acceleration and then time squared. So obviously we have no net change in displacement, so that's 0. This time we do have an initial velocity, 1,229 meters per second. We're going to leave time there because that's what we're solving for. 1/2 a negative 9.8 meters per second squared, and then time squared. So you should be able to take a look at this and immediately acknowledge that there is some sort of quadratic here. So we can do obviously some quadratic math. We're going to simplify this a little bit further though before we go ahead. 1,229 meters per second t. I'm just going to deal with this half and 9.8. So negative 4.9 meters per second squared t squared. So we can do a little bit of math here. We could factor out a t from our right-hand side. That's going to leave us with 1,229 meters per second minus 4.9 meters per second squared t. And of course, either t is equal to 0 or this component in the brackets, 1,229 minus 4.9 is also equal to 0. So we can solve this one simple here. T equals 0, and that makes sense because that's when our projectile motion started, right? It started at time equals 0. This second one, we can then go ahead and solve by saying that 1,229 meters per second equals 4.9 meters per second squared times t. If we divide both sides by 4.9 meters per second squared, we are left with t equals 251 seconds. So that is going to be how long the rocket stays in the air for, 251 seconds. Now that we have the time, we can start to deal with the horizontal component of our trajectory here. So we can start with our horizontal velocity, which is going to be 1500. This time it's times cos of the angle, so cos 55, which leaves us with 680.4 meters per second in the forward direction or in the right direction. And recall from the vertical calculations that time is 251 seconds. So this gives us enough information to solve for the horizontal displacement, which is also known as the range. So the range that a projectile travels is the same as the horizontal displacement. So simply, that gives us dx is equal to vx times t, which is 860.4 meters per second forward times 251 seconds. And that gives us a rather large number in the 200 and some odd 100,000 meters. So we can simplify that to 216 kilometers in the forward direction. Okay, make sure that your units make sense. If you're going to be in the neighborhood of 200,000 meters, well, you're probably better off using kilometers. Lastly, part C asks the maximum height of the rocket. So the maximum height of the rocket occurs when the time is exactly in half. So if the total time here is 251 seconds, half of the time, so time, and we could say time a half, for example, is 125.5 seconds. Because we all agree that a parabola, right, if this is the final time and this is the initial time, well, right here at the peak, that's half of the total time elapsed, right? So we can go back to our original vertical height equation, but in this sense, instead of solving when dx or dy is equal to 0, because that will be when it hits the ground, we're going to solve for dy, but we're going to use the same equation here. So we're going to say that v1y times t plus 1/2 a t squared. Substitute all our numbers from the previous slide, which are all the vertical components. So 1229 meters per second. We know the time, or we know at least what half of the time should be. So 125.5 seconds. I'm going to get rid of my drawing there just so that I have enough room. Plus 1/2 times the acceleration due to gravity times, again, our time squared. So if we throw that all into a calculator, again, you get something in the hundreds of thousands, so 77,000. So we're going to say 77 kilometers. And since it's positive, right, we know that is up. And of course, that makes sense, right, because the apex or the peak is going to be above the ground. So the maximum height of the rocket, 77 kilometers.